I can probably just
Everline.
I can. You need some coffee. Otherwise, you'll go to your workshops.
Come on, mate.
All right. Okay, let's get started.
Take it for us,
Let me have your attention. Let's get started. Welcome to the University of Tennessee Nuclear Engineering Department Colloquium Program. My name is Lee Dodds, and it's my privilege to introduce today's speaker. But before I introduce today's speaker, I should point out a couple of things. First of all, this is our last scheduled colloquium for the semester. Next week is the annual A&S meeting, and most of our faculty will attend that. The following week is the Wednesday before Thanksgiving. We know from past experience that's not a good afternoon to have a colloquium. And then the following Wednesday is study day. Classes have already ended. And so maybe we've saved the best for the last, Alan.
We'll find out.
We'll find out. Okay, today's speaker is Dr. Alan Wootton, who is the Chief Scientist with Physics and Advanced Technologies with Lawrence Livermore National Lab. Alan received a PhD from London University in 1972, and he joined the Oak Ridge National Laboratory in 1981, whereby he married a Tennessee woman, and there are grandchildren here apparently. And then he left Oak Ridge and went to the other UT, the University of Texas.
The one with the football team.
The one with the football team. Okay. Ooh. He was at the University of Texas for 13 years. When the football team went south, he left. And then he went to Lawrence Livermore National Lab, where he's been since 1998. The title of his presentation today is Laser-Related Astrophysics Research in Physics and Advanced Technologies at Lawrence Livermore National Lab. Alan, welcome.
Thanks. Sorry for the long title. So I actually have a real purpose in being here other than to see my grandkids. And that is that all of the national labs at the moment are really looking for new staff. If you look at the population in Livermore, the lab population, it's really quite scary. We're really looking for students to come and work with us. We're really looking for postdocs to come and work with us, and we're even looking for faculty to come and work with us. So I was trying to think of, with Soren's help, some topics that might be of interest to both of us. And, of course, it's going to be hard because you can already work with Oak Ridge National Lab, and Oak Ridge National Lab's right here, so that's the obvious place to collaborate with. But I don't think that Oak Ridge does very much laser-related research, and I don't think they do much astrophysics research. And so that was why I picked these two topics, which I'm going to go through. It will be very obvious as we go through this that I can't possibly have been involved in all this work. So I'm trying to give you a picture of the Physics and Advanced Technologies Directorate with lots of eye candy on the view graphs. As I say, the idea is to try and get you interested and to come and talk to me afterwards if you think there are possibilities for collaboration. So if we get this right. I'm going to start by telling you a little bit about Livermore itself and about the Physics and Advanced Technologies Directorate, including something about the people and facilities. And then, really, the talk is split into two. And I don't know how much I'll get through. I'm just going to stop at the end of 50 minutes, wherever we've got to. I'll start with the laser-related programs, telling you what lasers we have, something about high-energy density science, and then about light sources. There's some very exciting developments in X-ray free electron lasers. So I put that in because of its excitement, but also because it's about the only part in this talk I really know something about. Then, on the astrophysics program, I want to talk a little bit about our high-energy astrophysics research, both ground-based and space-based, and at least one view graph on the origins of life research, which we're doing. So let's move on. So, Livermore. It's a U.S. Department of Energy lab. It's operated by the University of California, and it was founded in 1952 as a second nuclear weapons design lab to promote innovation, trying to make devices smaller. The first device, this is a picture of roof tower after the first device went off. Not everything at Livermore has been successful. Think about what should have happened to that tower. There are almost 8,000 people, of which there are 1,200 PhDs. The annual budget is about $1.5 billion a year. Let's see. This is where it is. It's about 50 miles inland from San Francisco. Very nice place to live, very expensive place to live. What about the Physics and Advanced Technologies Directorate? That's what I'm in. It's one of a number of directorates in Livermore. It was created in year 2000 by combining what was then the Physics Directorate and the Lasers Directorate. The other directorates, to give you some idea of the totality of what the lab does, bio and biotech, so there's a big effort in biology and medical physics at the lab. Chemistry and material science, a large computation effort, of course, with the teraflop computer. You can imagine a large defense and nuclear technologies effort, probably taking maybe a half of the lab's funds. Energy and environment, engineering, and then you come down to lab services. There's also the National Ignition Facility, a very large laser which is being built, which has gone somewhat over cost and somewhat over budget. There's non-proliferation, arms control and international security, which is morphing into homeland defense, and that's becoming a big deal. There's physics and advanced technologies, which is what I'm going to talk about, and then there's safety, security and environmental protection. So what about PATH, Physics and Advanced Technologies? We've got a budget of about $140 million a year. There's a staff of 400 people, of which 300 have PhDs. 250 of those are in physics and 50 are in engineering. I think there are 40 fellows of the American Physical Society. This is really quite a remarkable directorate if you look at the people in it. It's clearly multidisciplinary, as you'll see when I get down to our 10-year themes. And it's got very strong research ties out to the rest of the lab, to many universities, and I'd like to make it at least one more, and industry. The mission sounds very generic. It's to be a leader in frontier physics and technology for 21st century national security stockpile stewardship, for homeland security, for energy independence, and for the exploration and use of space. And you might wonder why on earth Lawrence Livermore National Lab is doing things like exploration and the use of space. Hopefully I'll get into that, but it's because things like if you put a lens in the sky, you can point it up and you can look out, or you can point it down and you can see what's going on. So there are multiple uses for many of these things. We've decided on a number of 10-year themes. This is what the directorate is really pushing towards, where we're trying to recruit into. And if we have any free funds, this is what we're trying to spend them on. The first is creating and measuring matter under extreme conditions in the laboratory. You can imagine, of course, that the reasons for doing that are nuclear weapons related, but one learns some very interesting science about materials doing this. A new one is create a science-based homeland security program. A lot of this has got to do with detector technology, and that crosses into the space program, which is the next one, bringing our capabilities to bear on the exploration and utilization of space. We wish to make major impacts on biology and medicine using cutting-edge physics, and this is something I'm involved with. How could you use an X-ray free electron laser to measure at atomic scale any biological, and you really measure down to angstroms what's going on in cells, and we think we may be able to. Of course, what happens to the cell after you've made the measurement is another matter. develop a path forward for fusion energy. I've spent a lot of my time, my life, looking at fusion energy, and I decided that it really was getting further away each year. That's one of the reasons I moved. And one of the reasons I'm here, to recruit, retain, and develop the lab's next generation of leaders. We really want students to come and work in the summer. We really want postdocs. So, Pat, we've got a number of major facilities, and they will imply to you some of the research we're doing. And I think I've either got 4 or 5 on 2 view graphs here. The first research facility is our ultra-short pulse laser capability. There are actually 4 major and some minor lasers with energies from 0.1 to 10 joules for short pulses, and by short pulses I mean in the order of hundreds of femtoseconds, where a femtosecond is 10 to the minus 15 seconds. So these are short pulses, and some of them with rather high repetition rates, as high as 10 hertz. And one of those lasers is used to make an X-ray laser, and I've been using that myself to look at damage of materials, and we'll get into why I've been doing that. And I'll show you a view graph with some of the capabilities of these lasers a little later. We're very interested in, as I said from the start, materials under extreme conditions of pressure and temperature. And one of the ways you can do that is to shock them. And you can shock them either with lasers, or you can use gas gun facilities. So we have a 20-meter gas gun, and that projects a disc into an instrumented target at speeds up to 18,000 miles an hour. And for that, with those parameters, you can measure equations of state of interesting materials, which might be interesting to the nuclear weapons, which might be plutonium or uranium, or it might be interesting for its basic physics state. And you can get up to temperatures of 4,500 degrees K and pressures way beyond 1 million atmospheres doing that. Keeping going, yes, so I've got 5. Another 3 of the experimental facilities I want to talk about. We have a 100 MeV electron-positron linear accelerator. That's not a very high energy these days, but the question is, what do you use it for? So we have this radio frequency electron linear accelerator as a whole complex, and it's used for studying electron-material interactions, electron femtosecond laser pulse interactions, and in fact, if you take a visible laser pulse and you scatter that laser pulse off these high-energy photons, then you get X-rays out, and you can get up to 100 keV X-rays. And so, in fact, you can use this for what's called a next-generation light source. It's called a Thomson scattered source or a Compton scattered source. And so we are building and should have what we call first light this calendar year from this capability. And the linear accelerator also produces positrons, and you can use the positrons for material physics studies, rather like you can use electron microscopy, you can use positron microscopy as well. We have an electron beam ion trap facility. They're called EBITs. This is a facility that injects and then spatially confines very highly ionized atomic species, which you might want for high precision measurements. For example, we can get as high as uranium-92, and you can sustain these ions for many hours while you do experiments on them. And in fact, there are some plans through the lab-directed research and development funding to try and make some experiments to do with quantum computing using this facility. And the last facility I want to put up is one of the facilities we use for fusion research. It's a Spheramag. It's a machine which has some analogy to a smoke ring, not smoke and mirrors, but a smoke ring. And the idea is that if you could make this work, it might make a better fusion reactor. As I said, I've moved out of the fusion field, and I don't really want to discuss that too much. What are the new things we're doing? Those were the facilities we have, but of course we're developing new ones. Well, the most exciting facility at the laboratory is the National Ignition Facility, the NIF. This is 192 laser beam, 2 megajoules, and first experiments will be next February. So whilst this has been very expensive to build, it's about to start. Very exciting for the lab. You can imagine, of course, that when something goes over budget by a factor of 2, there are some fairly dramatic consequences for what happens to the rest of the lab. So it's been rather tight fiscally to instigate new research. However, a very nice aspect of national labs is that of all the money that comes in, the Department of Energy agrees to take off 6% before any of it is spent. And that 6%, which is called LDRD, Lab Directed Research and Development, then gets redistributed to the lab for basic research. And one of my roles is to decide on that basic research for physics and advanced technologies. So I actually have $20 million, which I spend each year, looking at new projects which we want to do. And that's where I'm picking those 10-year themes and allocating funds amongst those. And should any of you be interested in collaborating, this is where some of the funds could come from. We're also interested, for recruiting purposes more than anything else, but also laser aspects, in the next linear collider. This is a machine that may never be built, at least being considered. And some of the ideas now are not just that you would have particles hitting particles, but even you would have photons hitting photons, and looking at what happens with this. I'm going to talk more about the LINAC coherent source at SLAC. We'll come to that later. And I'm going to talk more about space-based X-ray work later. This is ground-based X-ray work, where we're collaborating with Livermore. And to talk about our collaborations with industry, we have had a collaborative agreement with various chip manufacturers to the tune of $250 million, where the lab plus Sandia plus the chip manufacturers have been trying to develop the next step in how you make microprocessors. So moving down to the extreme ultraviolet, where the wavelengths are smaller, so the feature sizes are smaller, so you can get more components onto a chip. So that gives you some idea of where we're trying to go. So now let's get on to the laser-related science in fact. Here are 4 of our lasers, which are currently working, and I use some of these. And they've got names Janus, Comet, USP, and Janus. And let's have a look at, for example, the wavelengths. And so this is in nanometers. Janus is the most energetic. It's got as much as half a kilojoule of energy. And you can vary the wavelength. You can take the first harmonic, the fundamental, or various harmonics. And this is a slow repetition rate. You have to wait for things to cool between shots. So you only get typically 1 or at most 2 pulses an hour. And you can get very high intensities. So we're talking about as high as 10 to the 17 watts per square centimeter when you focus this down. That's high intensity. And it's got a very good suite of diagnostics. The pulse lengths are not particularly short for this. They're in the order of 100 picoseconds up to over a nanosecond. Let's go to the other extreme, which is down here, the US and Janus devices. Now these have got short pulses, so we're looking here at 30 picoseconds. So that's 30 times 10 to the minus 15 seconds. That's short. That's tough to measure. It's tough if you want to get 2 things to arrive at the same time within 30 picoseconds. The energy is a lot less. It's maybe 10 joules, but the repetition rate can be higher. And the suite of diagnostics is actually less than it was over here because it's a lot harder to do. What's been of interest to me is the COMET experiment, where you use a short pulse laser to make a plasma, and then you can get inversions in the spectroscopic lines, and that will lase, and you can get that to lase in the X-ray regime. And so, in fact, this is used to make an X-ray laser, which I've been using for some experiments we'll talk about. Yes, if you want more details, the website, which relates a lot of the work done on these lasers, is at the bottom of the view graph. So this is a danger when you put a talk together a month and a half before you give it, and you get all your colleagues to give you these really pretty pictures, and then you forget about the talk, and you pick it up in the morning, and you think, what on earth is this picture? And you phone back to your wife, who's the secretary, to try and find somebody to help you, and it doesn't work. So some of these I'm going to talk about, and you'll notice I don't talk about all of them. It's because I've simply forgotten what the picture is. Now, the first one's exciting. I can even remember it. If you take a very short pulse laser, and you irradiate a very thin piece of material, maybe 100 microns, 200 microns thick, you produce a lot of electrons, a lot of fast electrons in the interaction of the laser with the plasma that you make. Those electrons leave the material, and as they leave the material, they pull out ions, and the ones they pull out first are protons. And so you make a proton beam. And in fact, if you bend the piece of material, like a lens, then the protons are emitted normal to the surface, and now you can focus those proton beams. But why would you want to do that? Two reasons. One is you can then redeposit those protons into a thin piece of material, and you can heat it to, I don't know whether electron volts mean anything to you, but to energy, you can heat that material to between 10 and 100 electron volts, which is an energy, a temperature of great interest to people that want to understand, for example, how nuclear weapons work, or, for example, how supernova work. It's the same physics. So again, you see this mixture between why Weapons Lab is involved in space research, astronomy. Another thing you can do with it is proton radiography. You've now got a very well-defined, fairly nicely energy-defined proton beam. And there's an example here. This is a capillary which is imaged with optical light, and here it's imaged with the proton beam. And this is a radial line out, and the units aren't on here, but in fact we've got 1 micron spatial resolution, which is really quite phenomenal. And this is, I won't say a tabletop device, but the whole thing would fit into this room, which is pretty good for a radiography device. The next one, I have no idea what the picture is, but it is very interesting to the lab to understand the equation of state of materials. One wants to know when certain materials melt. One wants to know what happens when you shock them. And so there are some very detailed experiments using X-rays. You use the laser to ablate a layer at the front of the piece of material. That produces a shock wave, and that then goes into the material and will increase the temperature, increase the density. You'd like to know when it melts. Well, if you have a separate X-ray source, then you can do scattering of the X-rays into that material, and from what the scattering does, you can tell exactly when it melts or when it doesn't melt, and you can compare that with models, and that's extremely important to the lab. Remember, these are all things we're doing with our lasers towards high energy density science. Something else we're doing, very important for the next few years, is diagnostic development for NIF. We have this suite of lasers, and it covers this vast array, huge array of time, really, from 30 picoseconds up to nanoseconds. And experiments on the National Ignition Facility really require new diagnostics at short timescales. And so we're developing new ways of things we call streak cameras, of how you streak images to understand what's happening on very fast timescales. I'm going to talk about this one more later, which was using the Comet X-ray laser to damage and to know what happens. And then let me just move over here. Relevant to supernovae explosions, again you can use lasers which heat gas-filled balloons, and if you get the densities right, you can do a simulated experiment of a supernova. Supernovas, of course, are rather large and take a long time to explode, but if you look at the scaling of the physics, then it turns out if you scale everything down to millimeters, and if you scale the time scales down to sub-picosecond, the physics equations are the same. This is called dimensionless scaling. And so, in fact, we can really do supernova physics on lasers because you can look at this scaling of how the physics laws work. So, moving on from the lasers that we're working on now, I wanted to quickly show you a little bit about the light sources which either involve lasers or are lasers that are coming up in the near term. And this, to me, is very exciting research. I think at least the one on the right is going to literally revolutionize biology and physics, and I'll show you why in a minute. But the one at the lab is useful for the lab, but it's not going to revolutionize things. It's this Compton X-ray source I was talking about, where you have bunches of fast electrons from our linear accelerator, and then you scatter off this light from an ultra-fast laser. It's visible light, so it's about 1 eV. And you get Compton scattering, and so you get X-rays coming out. So now you have X-rays which are in the order of 10 to 100 keV, and you can tune the energy. You can tune the energy of your X-rays by tuning the energy of the electrons or varying the angle of scattering. And this will be used. Remember, I was telling you it's very important to the lab to be looking at how materials react to shock waves. You needed an X-ray source. Well, here's the X-ray source for looking into scattering. Now, the one on the right, the LINAC Coherent Light Source, LCOS. This is what's called a fourth-generation light source. For many years, synchrotrons have been used to produce X-rays to do experiments. There is a new scheme, and it's now being built at Stanford, and Livermore is involved in this, to build a free electron laser as a light source. You take a high-energy beam of electrons, let's say 50 to 90 GeV, and you pass it through what we call a wiggler, a magnetic field that oscillates, and that's shown here. And so the electron beam, of course, oscillates as it goes through this wiggler or undulator. Now, if you can get the parameters right, and it's not trivial, people would have done it before, you've got to get the electron beam very tightly focused, and you've got to have a very short pulse. Then, as this electron beam wiggles, it emits radiation, just as an electron going around in a magnetic field emits radiation, synchrotron radiation. But if you've got the conditions right, then that radiation back interacts with the electron bunch, and you get an instability. And it's called self-amplified spontaneous emission, SASE. And if you do that, you get a dramatic increase in intensity in the X-ray radiation. And I've plotted that schematically here as the intensity is a function of distance down the undulator. And the bunch, the electron bunch, as I say, interacts with the photon, with the photons, and you get some quite remarkable properties, which, if I can remember the talk, I've got here. So here's a plot of brightness. That's the number of photons per second, per milliradian squared, per millimeter squared, per 0.1% of the bandwidth, which is a horrible set of units, but it tells you how bright something is. And it's plotted against year, 1900, 2000. And X-ray tubes, the first X-ray tubes were down here at 10 to the 6, 10 to the 7. And present light sources, like the advanced light source, are sitting up at 10 to the 22. And the device we're talking about making, because of this instability, is going to have a brightness of 10 to the 34. That's 10, it's actually more than 10 orders of magnitude brighter than any other X-ray source. When you go to a physicist or a biologist or a chemist and you say, I'm going to give you a new device and it's 10 to the 10 times brighter than the one you're using now, and brightness is what matters, they have no idea what to do with it. If you tell them it's a factor of 2 or 3, it's great, you'll get lots of answers. 10 to the 10 is a challenge. It's almost bright enough that if you focus this, you could boil the vacuum. It's really quite phenomenal. It's being designed and built at Stanford, and as I say, Livermore is involved, and Livermore's responsible for the X-ray optics, and they're a challenge, and you'll see why, and the X-ray diagnostics, and the X-ray transport, and some of the experiments. It's going to produce bunches of X-rays. Each bunch is about 100 femtoseconds long, so 100 times 10 to the minus 15. In that bunch, there are about 10 to the 13, I told you this is a bit I know about, which is why it's in here. There are about 10 to the 13 photons in each bunch, and you can tune the energy between about 1 and 10 keV, and with harmonics you can get up to about 25 keV. Now, other than build this because it's truly exciting, what's one going to do with it? There's a website you can look at, and it describes what we think are going to be the first experiments. This isn't going to be ready to operate until 2008, and so this list of experiments is surely going to change. And that's why I'm emphasizing it here, because if one's looking for collaborations and exciting things to do, to get involved with this, to do preliminary research based on this is great. I'm going to give you this list, and I'm going to talk about one in a bit more detail. Atomic physics. Well, this is the first time that, at least in a laboratory that is there after you've done the experiment, you can look at nonlinear X-ray physics to see what's going on. I talked about with a proton beam, using a proton beam to heat material to energies or temperatures between 10 and 100 eV. These can do exactly the same thing, these X-rays. But more than that, you've now got an X-ray laser with an energy of up to 10 keV. It's a laser. It's coherent. You can use this as a probe to probe solid-state material. So for the first time, you can do Thomson scattering into solid-state materials. The chemists are really interested in micron resolution and femtosecond to picosecond timescale resolution of how things change. The condensed matter physicists are intrigued by the dynamics of these nanoscale particles which they're looking at. Dropping to the last one for a minute, there's obviously the whole physics of the free electron laser itself. Does it really work like we think it will work? Well, people have now made, last year, an ultraviolet one of these, and the intensity was spot on the theory, after a little bit of changing the theory. But so I would say that every expectation is that this is going to work. It's going to be very hard, of course, because alignment, well, I think alignment is going to be crucial, but I think it will work. And the one I wanted to talk more about is the biological studies, one which I've got involved with. We think that you can look at the structure of cells up to proteins, and we think that you might be able to do that with a few femtoseconds time resolution, a few femtoseconds, and angstrom spatial resolution. Of course, we won't know for 8 years, and I'll be retired by then, but we'll see. So actually, the idea is really simple. And what limits you today in looking at biological particles is that you damage them. You need a certain number of X-rays to get your signal intensity, and if you put too many X-rays in, you just destroy the particle. But what happens if you can get the X-rays in to do your diffraction so fast that the molecule doesn't have time to disassemble? How fast does a molecule disassemble? Well, we think it's between 10 and 100 femtoseconds, according to our calculations. We've done some very sophisticated molecular dynamics calculations, and then we put that on one side and just ask the question, what happens if you take a molecule, the X-rays come in, they remove electrons, the electrons escape, so now you're left with a very small molecule which is positively charged, and now that explodes because of the positive charge. You get the same answer. So the molecular dynamics calculation was actually just calculating what we call a Coulomb explosion. And it turned out to be, it was remarkable that you could do such a simple calculation and get the same answer. So what happens is your very short pulse, has to be in the order of 10 femtoseconds, goes into this very small molecule. Your wavelength of light is sub-angstrom. You've got 10 keV, so inherently you've got angstrom spatial resolution. And the X-rays have gone through. They've carried the information on the scattering to your detector before the molecule or the cell has started to disassemble. So you've got your information. There are some challenges. 10 femtoseconds, but I said you've got to do this in. But the basic pulse length is going to be 100 femtoseconds. So here's a lovely example of where when someone finally says, yes, we've got an idea, you've got something 10 to the 10 times brighter, but 100 femtoseconds, we're not interested. Please give us 10 femtoseconds. So that's one thing we have to do. Another thing is, it's quite clear that as you drop this particle through the X-ray beam, which is the only way you're going to do it, it's of course going to be destroyed. and you're only going to get one diffraction pattern from each molecule. So you've now got to have a large number of identical molecules, and you've got to drop them in, presumably in random orientation, and each time you get a diffraction pattern, you've somehow got to bin the answers, so you've got to have enough information on one diffraction pattern to know into which of how many bins it's got to go into. So there's some really very interesting image reconstruction algorithms which one's got to work on here. And one can, of course, then test those. So here are some ideas for work that's got to be done in the next few years. Yes, so critical issues. We're working on the details of this short pulse photon material interaction, but it's by no means finished. There's the image reconstruction, and then we've got to compress the pulse temporally, but also spatially. I mean, we've got to focus it quite extraordinarily to get this. So this is a great idea, but a lot of work to be done. Now, this looks like a complicated graph, but it actually isn't. I've just talked about blowing up a molecule, and I said we had to somehow temporarily compress the pulse and spatially compress it, and you want to measure what goes on. Well, if you blow up a molecule, you might imagine that anything you put in front of the beam you're going to blow up, and that indeed is true. So if what I'm plotting here is the calculated, and this is based on a model which I certainly don't believe, but it's the best we can do right now. No, I've done that, I didn't mean to do that. This is based on a model for how much energy per square centimeter do you need to melt a material, and as a function of photon energy. And so this machine I'm talking about, the LCLS, the Linear Coherent Light Source, is sitting from around 1 to 10 keV. That's the photon energy. And depending on the material you look at, so for example, here I've got carbon. If you have 10 joules per square centimeter, at this energy, you'd melt carbon. If I had gold, I'd need less than 0.1 joules per square centimeter. Now, what's the LCLS going to produce? Well, even unfocused, right at the end of that wiggler or undulator, I'm producing 30 joules per square centimeter. So how on earth am I going to build any optics or any diagnostics for this machine? Well, one answer is, let's cheat. This thing, of course, has got a natural divergence. It doesn't. The light isn't exactly parallel. It's got a divergence, but it's not very much. It's only a microradian. So we're going to have to put some of our experiments kilometers, literally kilometers downstream, to blow this beam up so that the joules per square centimeter doesn't melt. But that's really a dumb thing to do. You've got this marvelous X-ray laser. One thing you like about it is its brightness, which means joules per square centimeter. And so what you're going to do, you're going to march downfield 2 kilometers. And then can you imagine trying to align things? So that really sounds hard. So we're looking very carefully at how can you build optics and diagnostics which will take very high frequencies. This again is something where I think a lot of research and work needs to be done. So one is, I showed you carbon. It had a rather high fluence to melt. You wouldn't have to move very far downstream. Low Z materials are better. So we're talking about lithium and beryllium. We'd like to make lenses out of lithium and beryllium. Here, in fact, is a carbon zone plate which we've made as a model of what we're going to make in beryllium. And this is rather intriguing. It's done on a diamond lathe. The dimensions are, that's 200 microns across there. The feature depth, it's actually a Fresnel zone plate for those that are interested. The features are 10 microns deep, and this was done on a diamond turning lathe. It's pretty neat. And this carbon one would not be of use to us, but if we can make one in beryllium, then it will be of use. Now, there are all sorts of problems one finds in beryllium. You find that the grain sizes are rather too large, but we're trying to work it out. Another thing you can do is to use grazing incidence. Here you can imagine the X-ray laser source, and it's reflecting off surface here, and if it's a grazing incidence where the angle is very, very shallow to the surface, then you can, and it's got to be very shallow before this works, like a degree or less. So then this has to be very long, like tens of centimeters to a meter. Then you distribute the energy over a large surface area. And you've got to be below critical angles, and that way we think we can do it. Then we had some great ideas that the funds ran out, but I'd really love to pursue these. How about liquid optics, which you could renew between each shot? So we actually took a microchannel plate, which has got small pores, maybe 9 microns in diameter, and you can force a liquid with a plunger through that, and of course the surface tension will keep the liquid to the shape of the microchannel plate, whatever you've machined it, and you can hold that in any angle. You can then imagine doing your reflection off the surface, and you pull the plunger back and you can renew the surface. Well, then we did those experiments and it worked. Well, then we thought you could get even more clever. If you could use a conducting liquid, you could then use electrodes to even shape the surface more than just shaping the microchannel plate. But as I say, that's not something which we've tested experimentally, but what a great idea. I'd love to build some of those. We also talked about using plasmas as a lens. So those top 3 and this bottom 1 are for lenses for spatial compression, focusing. What about temporal compression? Well, there are 2 ideas here, one of which turns out not to help but will work, and the other which will help but it's really questionable. You start off this machine by having a 50 to 90 GeV electron beam. But supposing you apply a small delta E across that, you call it a chirp, so there's an energy distribution across the beam. Then the photons that come out have got different wavelengths. And so, for example, in this one here, you've got red through blue representing the different wavelengths. Now suppose you take a crystal and you arrange that the lattice spacing in that crystal, where you're going to do Bragg diffraction, is spatially dependent. Not trivial. In fact, I don't even know how we're going to do it, but never mind. But if you could, then you could compress that pulse. It will, and in time, you can compress it by about a factor of 20, we think. But you do splay it out in space, and we're not sure of the ramifications of that. So that's a way of temporarily compressing, but I don't know how you make the crystal. You've got to make a crystal with a graded lattice spacing. Something you could do is time slice, where instead of trying to compress, you just pick out a certain slice. Again, you take this idea of chirping the electron beam, so your photon beam is multicolored, and you then have, for example, a zone plate, and then the different colors are focused at different points. And then if you put a grid in, you just pull out one color, and that corresponds to just one section of the beam. So you've pulled out a short part of the pulse. The problem with that is you've thrown lots of photons away, and you want the photons. So this is a very inefficient way of doing it. But you can see there's lots of opportunities for innovation and research here. I wonder if we'll get to the astrophysics. I can jump to it. Yes, I can. It comes after this, so we're going to be okay. So you can see a lot of what I'm interested in here is blowing materials up, and when do things melt, and when do they get damaged. And we have some theories that we, the government, is spending $200 million, which isn't much compared to NIF, on this linear coherent light source. And we need to know about the optics. And are our models correct? So we're trying to do some simulation experiments. How can I simulate the light source? Well, I mean, I can't actually simulate it, or I have it and I don't. But I can use our lasers. And I've started this program of work trying to produce conditions that these extremely bright light sources might make to see what happens to materials. One is to use this X-ray laser, the Comet X-ray laser, which I've told you about, and we've started work on that. The problem with that is that the energy of the photons in the X-ray laser is only about 10 eV. Visible light is, a couple of eV. I'm looking at 800 to 10,000 eV. So 10 eVs on the way, but just because I get an answer at 10 eV, I'm not really going to be able to sure I can extrapolate it. Well, I can make keV photons in the following way. If I shine a short pulse laser onto, say, a piece of aluminum or copper, then this produces fast electrons. Remember I told you that if I have those fast electrons and they escape, they make protons. But if the fast electrons don't escape and stay in the material, then I get Bremsstrahlung radiation. And so now I produce X-rays. If I could collect those X-rays and refocus them onto a target, then perhaps I could damage that target enough. Maybe I could get the joules per square centimeter here high enough to simulate what I need with the Linac coherent light source. Well, we tried this, and the efficiency of conversion was just lousy. It simply didn't work. So now we're moving on to trying this scheme, where I have my target to make the fast electrons and the K-alphas here. I've got the short pulse laser coming in, producing fast electrons. Fast electrons produce X-rays. The X-rays go on and damage this material here. Then I have a subsidiary X-ray source, and I look at Bragg diffraction off here, and if the material melts, then I'll see changes in what's going on. So we've done some of these experiments, and you can imagine what happens. I mean, this gets damaged because the laser light bleeds through, or because we produce protons, etc., etc. But this is a program of work which is ongoing and involves our lasers, leads into the light source, and we're extremely interested if people want to get come to the lab and collaborate with us on this. So let's move off lasers and talk a little bit about, for the next 10 minutes, say, astrophysics. I looked at everything on the web that we're doing in astrophysics, and it's quite remarkable. I'm not going to go through the acronyms for two reasons. One is some of them I've forgotten, the other is there's not time. But we're doing cosmology, looking at dark matter. Why is the lab interested? Data handling is extremely important for the lab, especially with regard to homeland defense. Focusing optics are involved, both in cosmology and in what the lab does, and detectors. We're looking at what I've called here physics of the universe. Supernova, black holes, various compact objects, and stellar evolution. Why is the lab interested? For many of the same reasons, but some slightly different ones as well. Focusing optics, detectors, and also codes. The codes between how a weapon works and how supernova explodes are remarkably similar. And we're also looking at the physics of the origins of life. It's intriguing. One of the ideas for how life started on Earth is that comets carrying certain chemicals with them on impacting the atmosphere undergo a shock wave, and that shock wave produces very high temperatures and pressures, and under those temperatures and pressures you can get some very interesting chemical reactions, and we've been simulating those with our gas gun and got some very unexpected results. And there are other reasons here, but I'm going to move on. So I'm going to look at just a few of these to show you the sort of thing we're doing, the sort of areas where if you're interested in astrophysics, where you could come and collaborate. And the person that does a lot of this is somebody called Bill Craig, who actually started his PhD here, but left because there wasn't an astrophysics program, went to Santa Barbara, and will be very happy to come back and specifically give a talk on astrophysics to UT. So we are involved in this billion-dollar mission, which is meant to fly in 2008, to look at 1 kV up to 40 kV X-rays and gamma rays coming from space. And the idea is that one will have 4 satellites at different locations, and those will be connected together to make effectively one giant telescope looking at this energy range. And this is a remarkable thing. It's a big step to do because optics have not yet been flown successfully, I understand, at energies greater than 10 keV. And so this is something which is being prepared now. We're now looking at the optics for this. As a precursor to that, balloon-borne hard X-ray focusing systems are now being built. And in fact, we had the 50th anniversary for Livermore, I think it was back in September, and this was one of the major exhibits, this large balloon-borne gondola. So the idea is to produce, for this case, 9 colour-lined hard X-ray telescopes, and they're going to do this looking at 68 keV photons. And you can imagine that here the problem isn't just making the optics, but when you've got this thing floating around up there, how on earth are you going to keep it pointing in one direction for the accuracy that you need? So there's some quite phenomenal feedback systems required to keep things stationary. And I put at the bottom of this talk many of the websites where you can get far more information than I have time to go into. But again, we're building detectors to this, and we're also building some of the optics itself, and that's going on now. This addresses the optics. At energies up to 8 kV, which is like the Linac coherent light source, you can use this grazing incidence technique to do it. But you have to build shells up like this to get the effective area up. People have said that you could in principle do this at tens of kV, but the expense would be enormous. It would have to be so large because the grazing angle has to get smaller and smaller, and so the surfaces have to get larger and larger. But there is a solution, and let's go straight to this one, and that is that you use graded multi-layers. This is very similar to what I was talking about for LCLS, where one wanted to have a crystal whose lattice spacing grid changed with space. This, in fact, is exactly the same idea, but now you can reflect with rather high efficiencies many colors, and you don't have to, because the angles can be much larger than for natural reflection with these systems, you can now make much smaller systems, and we think those will work. So the lab is involved in all of this. We're also involved in what's called the EXIST mission. For this, we're building ourselves cadmium zinc telluride arrays. A very exciting diagnostic because they're extremely sensitive with very large surface areas. This will be flown, but why are we interested in this? Well, these CZT detectors will pick up radiation from nuclear materials. And so if one's worried about homeland defense, here's a possible detector that you could use. They're so small, in fact, that somebody has managed at the lab to fit one of them into a cell phone. And so now you can imagine equipping police, etc., with a cell phone that is automatically every 30 seconds checking for various radiation at certain frequencies and transmitting the data back into a database. So you can build up a data of it. The first thing you find is when somebody's just been for a cancer therapy, you get false readings. It's true because they've tried it. But you can now build up a database and you can start looking for sources that shouldn't be there. So here's an example of how a detector being used for space is also feeding back into homeland defense. And the last thing, just one last view graph, this was on the origins of life research. The supposition was that shocked liquids, shocked amino acids, might have been brought in by comets. Now, why they're on the comet, I can't explain to you, but experts in this bioastrophysics assure me that all the comets they've looked at have these amino acids on. So, a series of experiments was done at the lab using our shock experiments, the hypervelocity shock tube, to simulate a cometary impact. And so the bullet was now hollow with some amino acid in, and only amino acid. And after the simulation of the cometary impact, they analyzed what was there, and they found many new chemicals, many dipeptides, which are the essential components of proteins, etc. Now, the experiment's only been done twice, and one really worries now about, is it the pressure that's done it? Is it the temperature that's done it? Were there some catalytic effects of the walls, which obviously wouldn't be there for a cometary impact? But if this holds up, this is really quite exciting. So, last few graph, and I'm sorry I've been a little too long. Physics in Advanced Technologies is working on projects that I hope might interest you, and I would love for people to collaborate with us. And I've shown you some examples where I think we're different from Oak Ridge, which is obviously your natural collaborator. And they are the uses of laser for high energy density plants work, light source development, and everything that attends that, this linear coherent light source, I think is truly exciting. Astrophysics, which includes the origins of life. Thanks very much.
Thanks. One question, and then we have more questions downstairs. Continue to ask questions, comment. Dan?
Have you actually created these multi-layer, or has anybody tried to create these multi-layer diffraction crystals that you've talked about for compressing the temporal information?
They've been made using a laser to shock a crystal. And as the shock wave goes through the crystal, you change the lattice spacing. Of course, that's temporary in itself, and it's not clear how much control you have over it. But it's clear it worked because by doing Bragg diffraction at the same time, you could see things change. It would be much nicer if you could do it by growing things with strain. And I don't know if that's been done. I think that has not been done. I think it's to be played for.
Okay. I do see some new faces in the audience. We have new faces every week. And the new faces probably do not know that we do have refreshments downstairs and that everyone is invited. But before we adjourn for refreshments, let's express our appreciation again to Alan.
I'm kind of keep up. I we enjoyed being heard your host.
Oh, okay.
Maybe one minute. I really hope it happens. Maybe.
I'm not